All right, let's get started. So last time I sprang on you a whole lot of rheology models. In other words, mathematical way to describe a very donkey fluids. And when I say very donkey fluids, we mean a non-Newtonian, something that has a complexity in which the resistance to flow will change with how you flow. So that we quantify with the shear rate. So if the shear rate or changes in velocity in space are changing or large or small, so for large ones and small ones, we're going to have a different resistance to flow. So what is something that you do remember about any of those non-Newtonian models that you specified? What are some examples? Some examples from everyday use. Toothpaste. So what's specific about toothpaste? I'm gonna stress it out. It's not gonna start flowing out my tooth. One of these days, I was gonna engage with air people, TSA people, in a discussion whether toothpaste is actually fluid. But I haven't dared so far. It is a combination of solid and of fluid, and you could kind of view it both ways. It behaves as solid as long as the stresses on it are less than this yield stress. And then when you have yield stress, it starts to flow. So it depends on the day. You kind of can refer to it both as fluid and as solid. I did not dare to engage in a conversation just yet. But one of these days when I travel with more than 3 ounces, I will try. Anyway, I will report that. So let's catch up ourselves. What are some other behaviors that are very specific of polymer but could be of anything else? As I start increasing the flow rates and the shear rates, what can happen to it? It can thin or thicken, and that's basically this resistance to flow changes. What is the molecular mechanism that is involved in that? So it's good to visualize with polymers. We have these large chains, polymer chains. They're not your average molecules such as methane or water molecule. They're very large chains. They have a complexity. They kind of move around. I like visualizing them literally like here. And then sometimes, as over here, under high shear, the shear can straighten out and align. But sometimes it doesn't. If I have different types of different polymers, and often we'll load the fluid on multiple times, they might kind of cross-link and combine. It becomes more difficult to flow. So sometimes I'm going to thicken, sometimes I'm going to thin out if I align and just kind of straighten out. Blood is a similar thing. It has platelets within. So at higher rates, if those platelets align, you're going to have shear thinning. But if they start crossing each other and building some sort of more complicated stuff, then it's going to shear thin. So it depends on the type of the intermolecular forces that you actually have between these large things. Okay? So any kind of charges that come into play might make things more complicated. So those are some of the molecular mechanisms that are kind of good to think about. Now there's no perfect model for all of these behaviors. We kind of have a range of models. So I threw a whole bunch of models at you last time. What I mean by non-linear when you start working on the homework. Has anybody started? Maybe not. Well, so the basic thing is that you're going to get either in description when we were describing things. Let me go to the slides. We would either plot shear stress versus shear rate. So this is what I refer to as tau yx in my formula. So if you want to remember any formula that you should remember, to remember quickly is that Newtonian fluid between two parallel plates. Tau Ix is minus mu dx dy, right? If I think about that, in that formula, let me get to it. Basically, shear strain rate, or gamma dot, is minus dvx dy. So what this says is that shear stress, tau Ix, is mu times gamma dot. Yes? So it's proportional, and this mu for a Newtonian fluid does not depend on the shear rate. So Newtonian fluids are nice, mu is a constant. In more general case, that's not the case. So we introduced a whole bunch of other fluids. So for instance, Bingham plastic. So Bingham plastic says that tau Ix is, for these stresses that are large enough, it is minus mu 0 dvx dy plus tau 0. So get a pen and pencil. So tau Ix is equal to minus mu 0 times gamma dot. Is that correct? Plus tau 0. If I wanted to express that in a general form, tau Ix is some function, and I'm going to now say eta, referring to this viscosity as some sort of non-linear thing, that is possibly a function of a shear rate, times shear rate. How would you transform this to this form, and what is an eta? So I know that tau Ix is, I'm going to write tau 0 minus mu 0, or plus, I'm just going to write it this way. Everybody agrees with this from that formula? Yeah? So then just take that gamma dot out. Silent. Charlie Chaplin. No sound in this video. Can we do a comparison? This is my function of the shear rate. So that's my viscosity. And it changes with shear rate. So sometimes for these and I actually mixed it all up in the slides, and everybody was just like going along last time around. So now I want to kind of bring it home, because when you start fitting the data that you got in the homework, you need to see the difference. So sometimes we will be plotting tau Ix versus gamma dot, right? So this is shear stress versus shear rate, or shear strain rate. Sometimes we will actually plot viscosity versus, and this is the generalized viscosity that depends on gamma dot. So it's viewed as a function of gamma dot, right? And I could spring any of these plots on you, and I did, without anybody raising a question last time. So I want to straighten it out before you start looking at the data. Now, generally speaking, if I have a plot of shear stress versus shear rate that comes from a viscosimeter, then the slope of it, which could change with the shear rate, but the slope at every point of the shear rate is basically what gives me viscosity, right? And for Newtonian fluid, it's a simple constant that is same everywhere. So if I have a straight line, slope is same everywhere. Anything else, slope is not straight, same everywhere. So I find it as a slope on that graph if I'm just drawing things to myself. But I could also plot this versus shear rate, right? And then shear stress I would get like at every point by multiplying the two. Yeah? So let's see which plots we have in this graph now. So basically here, this is shear stress versus shear rate. So here I have a tau zero effective viscosity, but basically it would be my functional relationship there for a viscosity as a measure of shear rate. So slope is constant in this plot, but I do have an intercept because I don't start at 0. So nothing, this is the expression of the fact that nothing starts unless you actually have a yield stress going, and then things are moving. Okay. Now, what are other plots we have? So here, this is what was a parallel fluid. So maybe you want to start actually make yourself a table. What I intended to write on slides, but oh well, my garage is not in the garage. I think the name of the culprit is Dario, and he's 5. Alright, so you can put like a fluid, and maybe we can do shear stress versus strain, and what is eta as a function. So in Newtonian fluid, I have minus mu dvx dy. Minus dvx dy is what we refer to as shear strain, right? So this is Newtonian. And then my eta is constant, right? For Bingham plastic, I have this, well, if tau yx is larger than, if I actually have things flowing, then tau yx is tau 0 plus mu 0 gamma dot. And my viscosity sort of function from that, if I'm just looking at it as an effective viscosity, is this. Now for power law, my tau yx is minus m gamma dot to the n minus 1 times gamma dot. It's really minus m times gamma dot to the n. But I want to conform to this so I can express viscosity. Plus, because gamma dot is minus dvx dy. Is this okay? Now, what difference does it make in fitting the data? Do we remember how to curve it? Maybe. Maybe. I'm going to express it as the following. I'm not going to go into linear squares, the least linear squares fit and how what is the background of it. I'm just going to assume that given data, sets of data, xi, yi, data, endpoints, some set of points, we know or have a function that fits this data into linear model, or also known as linear regression. That says, hey, I can fit this into a model. Y is A0 plus A1x. What that means is that given some bunch of data, I can spit out a line. And A0 is the intercept, and A1 is the slope. Yes? Let's assume I have a function. You do have a function. Go to your 310 notes. You don't have to go to your 310 notes for the purpose of this class. You go to what you're comfortable with. We did cover this in 310, so if you did it in Python, you can do it in Python. If you did it in MATLAB, you can do it in MATLAB. If you really, really don't like those, but you enjoy Excel, you can find this in Excel. Just don't expect me to help you with it. I'm better in the first two. Okay? I don't like Excel's programming environment, but that's just a personal choice. If it works for you, it works for you. I don't care. For the purpose of this class, you need to know how to use something to help you out. Now, I just want to put things in perspective and how we fit this data that we actually now really care about for transport purposes. If I had a Bingham model and somebody gave me shear stress versus shear rate, that's an obvious linear model, right? Tau 0 is the intercept, mu 0 or mu, however you want to call that one, is your slope. Case closed. You take n points, n measurements that you have into your favorite function that does linear regression and gives you intercept and slope. I'm referring to them as A0 and A1 here. Yes? Cool. So we just assume we have that function. That function exists in all types of software you could possibly imagine. And then you have a model for it. Great. If somebody gave you viscosity data, right, versus shear rate, you could transform it to this, right, and then fit. But you need to know these relationships to do that, so it's a little bit of math. Great. So Bingham case closed, that's linear regression. What about power law? So say somebody gives me tau yx, shear stress versus gamma, and my model for power law, assumed model, you have to know what you're assuming before you fit, is n gamma dot to n. I'm just going to simplify that. Because somebody gave me shear stress versus this. How do we linearize this? Do you remember? Log of any kind, ln, log 10, doesn't really matter. Then log of tau yx is log of n plus log of gamma dot to the n, which is n log of gamma dot. Yes? What is now linearly related in this? What's real? What new variables, form some new variables that are linearly related in this class? Call this y tilde. Call this x tilde. Then y tilde is your A0 and this is your A1. Yes? This is like power law relationships on a log-log plotter, a straight line. Power law relationships on a log-log plotter, a straight line. This is why. Yes? And the joke is, if you cannot fit something to a power law, you haven't tried for long enough. If you can always find parts of my range where power law is valid, so you can be sort of piecewise power law, if you like. It's kind of the most common fit, and it's easy to just work this way. So you can actually go to parts of data and fit these relationships to parts of data. Great. So basically now, if I'm in my computational software, I create log, whether you choose ln or log 10, couldn't care less, or log 7. Pick your favorite base for logarithm. All the shear stress data that you have is equal to, and then you create log of your shear rates, and you run your linear regression function to give you A0 and A1. And I think it should be obvious enough how to get M and N from A0 and A1. A little bit of math. Yes? As long as you got Bingham and power law assignment, your life is easy. It's those 3 and 4 parameter models that gives us a little bit of headache. What are the ones? So we said basically, okay, great, Bingham and power law are great. It says that fluids might exert both of these things, yield stress and power law behavior, in different proportions. And then I get these combinations, or a little more complex models. So, these are the plots. We went through this. So this is shear stress versus shear strain. So we said, okay, for one thing, depending on the range, I might actually see different behaviors in different ranges of shear rate. So that is common. Or I might have something like this. Herschel-Bulkley is a pretty common model. In that one, I'm saying I'm expressing viscosity now. And I'm going to combine the last two lines in case, so this is Herschel-Bulkley. Also, in case where my shear stresses are larger than the yield stress, I'm putting absolute values here. For now, don't worry about the sign of the shear stress. That is something really that is specific to the coordinate system you pick. It kind of depends how you're oriented, and if there is your solid surface, we're measuring shear stresses on solid surfaces, that's where they're maximized. And it kind of depends how is that solid surface oriented. So really, for these type of data, fitting this type of data, just assume it all positive, don't worry about it. And you will get it all as positive. Okay, so we are saying, hey, this viscosity, effective viscosity, is m gamma dot to the n minus 1 plus tau 0 over gamma dot. So if somebody gave me shear stress data versus gamma, what is its relationship? I give you this on the slides. How do I get tau by x? I multiply with shear rate, gamma dot. Yes? This is your general relationship. You just replace this with, where was it? Okay, write it down. So I'm going to write it down now. This is the generalized form. Right? This is the constant for Newtonian. So what is it? I just multiply that thing. So I'm going to basically get m gamma dot to n plus tau 0. So I can recognize now this Bingham behavior. I'm just not doing a constant here. I'm doing a power law here. shift the power. Yes? Questions? Again, sometimes you will get viscosity versus shear rate, sometimes you get shear stress versus shear rate. You kind of have to be able to juggle between the two. This is the general thing that is, so this is my generalized viscosity, effective viscosity, that relates the two. And we think about shear stresses in the most simplified way as my fluid between two parallel plates. I have only one velocity, and that one is in x direction, right? And it kind of depends on y, so it's a function of y, which is why I actually do dvx dy. The others don't exist. Zero. And I'm going to complicate it for you a little later, but right now this is the best way to think about it in a parallel plate model. Yes? So how are we going to fit that data? This model, Herschel-Bulkley, has 3 parameters. Technically, no matter what somebody gave me, let's say that somebody gave me shear stress versus tau yx is n gamma dot n plus tau 0. And now I have to do 3 parameters. If I do my standard log business, then I kind of have to do this. So this combined thing, this can be linearly related if I do log of it. The only problem is that I don't know tau 0. What would be sort of one thing to do? Basic engineering solution to anything. Trial and error. Okay? Guess tau 0. Go with it. Calculate how well it fits. Remember that we can do that R-square measure in linear regression. That will tell you how well it fits. Then take another guess. See how well it fits. Then take another guess. See how well it fits. Pick the best out of the guesses you've made. Okay? How do I take an educated guess? I look at the data. Yes. So I plot myself shear stress versus shear rate. Try to guess this tau 0. Now it's not linear relationship. It's this, right? Somewhere in there. It is sensitive to that choice, but that's what gives you range. So if these were the units in dynes versus this is CGS system, then guess somewhere around 200. And how do we computationally deal with guessing in a more structured way? Give yourself an array of guesses and run a for loop. Record what is your goodness of the fit given by that R-square measure for all of them. Pick the best. But there is nothing wrong with trying 4 values by hand and checking it out to test it out, get a feel. And then in a structured way, you write a for loop. Okay? You can get your computer working, do it yourself. If you're doing it yourself, do 3 to 4 guesses. Okay? You're getting and you're using the calculator or whatever to tabulate this. But otherwise, do a guess. That's one strategy. So for your homework, I suggest that you all pair up and discuss these options. Try different things. Just try different things. It's not an exact science. If you make it exact, it becomes sort of like somebody's master's thesis, pretty much. And you kind of figure out a strategy that works for you and gives you pretty good. Okay? Why it becomes, because whatever you come up with for the data that I gave you in homework, next time somebody will show up and give you shear stress in different units. They're like 5 times larger, and now suddenly whatever picks you made by hand will not work, so you have to work with that, okay? So not all strategy will work always with all data, so just be okay with that, because data comes in different ranges. Yes? So pair up. If you find resources, Excel, online Python solutions, online MATLAB solutions, I'm fine. Tell me what you're using when you're doing the homework. And how are you using it? We're good. We're not, like, I want you to understand what's behind it, because this is something that was covered in 310. And when you have to pick strategies, you kind of have to do these linearization steps and understand how it's done. But beyond that, if you find something that works, okay. So in Python, there's a scipy.optimize that has a range of these linear regression, nonlinear fits tools. Feel free to explore them. Or in MATLAB, same thing. I did not, I think well, in 310, in either MATLAB or Python versions, I did not focus on using tools that exist. I focused on you understanding this process of writing. If you want to go to your linear regression code from 310, by all means, I can post it for you. If you forgot where it's at, just let me know. Anything works. Anything works. Use the tools. Here we want to use the tools. You find the tool that you're comfortable. If you, again, find Excel choices with Excel solver that work for you, by all means. Yes? Questions? Does it appear remotely? Can I get you to learn this again? So, recap. It's important to remember this generalized relationship. We might be given shear stress versus shear rate data, or viscosity versus shear rate, and being kind of agile and going back and forth is important. So you can figure out if you're fitting the data, so you can figure out how to linearize. Now, we also mentioned 2 more models, Cisco and Cross. I'm not going to go over them in this. You can now do this exercise yourself. But basically, Cisco model, I give it as this effective viscosity. So I would multiply it with gamma dot to get shear stress versus gamma dot for this model, right? Depending on how data comes in. And again, pretty good strategy in this one would be it's 3-parameter model. Guess one of them. So this behavior is this one here. So for large shear rates, see where it plateaus, and that's a good guess for this one. And then just run a number of guesses and see which one fits the best. Similar to Herschel-Bulkley. It's just there we were guessing shear stress, or yield stress rather. Here we are guessing this viscosity
that as the shear rate goes to infinity, so sort of like asymptotic behavior of viscosity. And then cross model, it has 4 parameters. It has a little portrait again, you would guess these asymptotic behavior from the graph, from the data that is very close to here. And then you go with that. Yes? Whatever other tool you find, again, in whatever software of your choice, by all means, use it. All right. So this is one example for the data. So here you can see how this would be for the data range here. Like this would be a good guess for that eta 0 in cross model. Yes? And over here, somewhere in between these two is a good guess for eta infinity. And those two guesses I try, and then I try. And then the cross model is a pretty good fit to this data. Okay. And the Cisco model doesn't do it well. And the power law model doesn't do it well either. Yeah? Questions? Everybody's like, oh my goodness. You're not ready for this. Okay. All right. Now, no worries. There are more models in literature, so all of the list that I gave is not exhaustive. It's just a pretty good list. Okay? But as different fluids are engineered, they might require simply whatever existing models you have, give you something like the power law here, or Cisco, and that's not good enough, and then somebody came up with cross model. And then you come up with a different fluid that does different things because it's a complex mixture of both particulates and polymers and all kinds of additives. And a different shear rates that does different things. So you come up with different, that's how in literature you have a range of other models. Okay? But this group that I give you is a pretty good group. Okay? All right. And we will not go into this time behavior where things and viscosity are changing in time and have sort of like a history built into it. So we will get to this a little more, but we measure viscosity with different type of viscosimeters. Ultimately, there's sort of, you can't do infinite plates in the lab, so we do these cylinders that rotate, and we're going to solve for this, so we will see the equations in work. And the equations we solve for we basically use to estimate the total shear stress on these solid surfaces, and that gives you the estimate of viscosity. So just like in any measurement, there has to be a good model behind that gives you the equations, so you can, whatever it is that you measure, you can basically express with those equations and give the numbers out. Okay. So I'm not going to go through this in class, but there's an example for ultimately, oftentimes, if you do a quick measurement, you're just going to get this effective viscosity, which is essentially this number. So it's given for a given shear rate, this number is constant. And in that sense, we're talking about it as a effective, and definition of it is that effective viscosity is the viscosity of a hypothetical Newtonian fluid that would give the same shear stress. Right? But that's kind of fixed only for the shear rate, and then the moment you change the shear rate, well, effective viscosity changes. Okay? But if you know that you're running something at fixed shear rates, you can model your non-Newtonian fluids as Newtonian if you kind of freeze the shear rates, or for certain range, you know, it's a good approximation. So nothing wrong with approximations. And this video that is linked here in the slides will give you how to actually just estimate the effective viscosity with Marsh funnel in the field. Quick measurements, you didn't send anything to the lab, you just get an effective measurement. Okay? All right. So let's go back
to our viscosity model and our velocities and recognize that no, we don't always have a simple velocity that is only in one coordinate direction. We have a generalized velocity field. So here I have my Vx. All other velocities, Vy and Vz, are 0. So I only have one non-zero over Vx. And that Vx in the parallel plate model changes as I change my y coordinate. It doesn't change with x. It doesn't change with z. Are we okay with that? So it's really just Vx of y. And the only derivative that exists is dvx dy. All others are 0. Now, what if that's not the case? Okay. So basically, in general, I have a three-dimensional system. In this coordinate system, x, y, this is my y plane. Note that this y plane was one of these plates. Any plate parallel to the plates I had was a y plane. And a y coordinate vector is orthogonal to that plane. So the way we characterize planes is by any point, let's say my watch is a point, and a normal vector to it. It doesn't matter what is the direction of this vector. It could be down, it could be up. That gives me kind of orientation, which side of the plane I'm at. Okay? So in this case, if I have any of these plates, I'm orienting things in the coordinate system such that my lesser y values are down and higher y values are up, and my y coordinate vector points towards the larger values. I could have oriented my y down. That's an option I have. But once I pick an option, I gotta stick with it. So in this option, then what we visualize as shear stresses, we recognize that overall x momentum of the bottom of this, lesser y values, is larger than the top. So that's what's shearing the top. That's the force that the top portion, if I divide this into boxes, the top box is feeling anywhere I place my plane. I can feel that the bottom part of it is shearing the top because it has larger velocities overall. And that's the shear stress. So shear stress is this x momentum. X momentum is rho Vx in this case. And it's transferred across y plane. So that is basically transfer of rho Vx or x momentum across y plane, and we denote it as tau yx. Now, what if I have different planes? Okay, I could have actually some general velocities and general velocity vector that has Vx, Vy, Vz components. And all of those momenta, x momentum, y momentum, z momentum, could transfer across my plane. They do transfer across y plane, x plane, z plane, in any plane I feel like striking. But what we need to describe overall stress state is just 3 coordinate planes, because I know that in the 3-dimensional world, when I place a 3-dimensional coordinate system, any vector can be expressed as a linear combination of those things. Yes? That is the whole point of coordinate systems. So to actually describe the stress state or shear stress state, I need how all of these momenta, x, y, and z, transfer across 3 planes, x, y, and z. 3 times 3 is 9. Are you stressed yet? So we have 9 versions of this tau yx.
when I'm looking at just this y plane that I start here in the general 3D, okay, then I have basically x momentum transferred across y plane is tau yx. That's what corresponds to my rho vx x momentum. Then I have y momentum transferred across y plane, and z momentum transferred across y plane. So I have a vector that describes how my xyz momenta transfer across y plane. And then similarly, I have tau x and tau z. Those are vectors that describe how x, y, z momenta transfer across x plane and z plane. When I put these three together, I can put them into a stress tensor, into a matrix. And that is my generalized tensor. Now, one thing to do, and that's going to be my parting thought, we're going to continue this next time. Basically, in this description, I do have x, x, z, z, y, y. Okay? So let's stick with that y plane. Let's say that I have some y velocity, so I have some convection going in between my two plates. Okay? So basically, then I'm going to have my overall fluid layers also have this y velocity. Okay? Some of that momentum will transfer across y plane as well. And that in itself is a normal stress. It acts like this. It's not shearing. Right? So these are all viscous stresses. They happen because I have differences in velocities, but some of them are normal stresses, normal, and some of them are shear, just in terms of direction. So these x, x, y, y, z, z are normal stresses, and the rest are what we refer to as shear stresses for this one. Right? Yeah? You are stressed by now. Okay. All right, well, we will continue this on Friday.